All right, so starting from the beginning again. For my last lesson, we know we have a compound interest formula. The amount is equal to the principal. That's the initial amount. You can also think of this as a sub 0, right, times 1 plus. So normally, for exponential growth, it's just 1 plus the rate, right, to the t power. But when you compound by some frequency, we have to split it up by however often we're compounding. So let's say we're compounding monthly, then n would be 12, right? We raise that to the n power. And all of this, that's going to be what you're actually multiplying by once you take into account compounding, right? And we can use this entire thing to figure out essentially the APY. And that's like the actual interest after you take into account how often you're compounding. And that was our compound interest formula, right? And so this R here, that's the rate. You can think of that R as the APR. That's usually what a bank is going to advertise for like loans and things like that because it's lower. But after you take into account compounding, then you get the APY. Right, so Carla wants to start a college fund for her daughter. She puts in $63,000 into the account. So that's our p-value. That grows at a rate of 2.55%. Right, that there is our R, or the nominal rate. And it's compounded monthly, so n is equal to 12. So a function to represent this would be the amount she put in, 63,000, times 1 plus. So we got to change that R into a decimal, move the decimal point 2 to the left, divide by 100, 0.0255. So what a bank does when they're compounding monthly is they're going to take this yearly interest rate and divide it by 12. So they're going to apply 1/12 of the interest rate 12 times once a month, right? So over the course of the year, they're going to apply that interest rate 12 times. So we could use this again to calculate the APY if you wanted to. But this is what we're multiplying by each year. So it's really all of this raised to the t power, where t is in years. But we know a power to a power, we can just multiply those exponents. So that's just 2 to 12t. Right, is that good? So graphically, if we're finding a number of years, it would take the account to reach $100,000. We're really trying to solve this equation. $100,000 equal to, right, because that equation I wrote represented the amount of money in her account. So we're really just trying to solve this equation. There is an algebraic way to solve this using logs, but we haven't learned logs yet. So we do it graphically. So when I sketch this, I'm going to be sketching, well, this is going to be my t-axis. This would be the amount of money in the account, C of t. All right, I'm going to sketch $100,000 and see where that intersects my other graph. So when I graph it, I know it's going to be exponential growth. And I'm really just looking for the point of intersection. So make sure you can do this on your TI Nspire. But I will be doing this on Desmos. So how do I do this again? New share. Let me change the screen. All right, can you guys see my other screen now? Do you guys see Desmos? All right, cool. So I'm going to be graphing y equals 100,000, bam. And of course, you don't see anything. And I'm also graphing 63,000 times 1 plus 0.0255 divided by 12, all raised to the 12x power, right? And of course, I'm not going to see anything because you have to adjust our window. So if you're on your calculator, probably adjust the Y values first. I know I'm graphing $100,000, so I'm going to go up from like 0 to $150,000 at least. There we go. I see some lines, and I can't see where to intersect, so I need to increase my X values. So if you're on your calculator again, you go to Window Settings, and I might go from like, I don't know, -10 to 50. And boom, that's where it intersect right there, 18.138, comma 100,000. So that point of intersection, 18.138, comma 100,000. And so it takes 18.14 years approximately to have that account gain interest such that it accrues to $100,000. Should probably switch back to my iPad. But also on Desmos, what's cool is you can, if I just take a look at that, right, this value over here, that is 1.0258. So if I ask you for the APR, again, this is the expression you would use to find APR. It would be 1.0258 or 2.58%. So a nominal rate of 2.55% when compounded monthly gives an effective rate of 2.58. So let me go back to my iPad. All right. So that was from the homework. There's another homework question pretty similar to that. So I'll post up an answer key. So that was compounding monthly. What I want to talk about today is compounding continuously. So what do we mean by continuously? So the more, oh, I'm not sharing my screen. Hold on, resume share. All right. So what I want to talk about today is compounding continuously. So the more frequently we compound, we know the better and better return we get. We get more money the more often we compound. So what's going to happen if we compound continuously? So we can compound like monthly, daily, we can compound every hour, every second, every millisecond. So continuously is like compounding all the time, an infinite number of times. And let's see what happens. So an account starts with $1 and they pay 100% interest per year. So this is just some thought experiment. So if we have 100% interest each year, if we're compounding annually, only once at the end of the year, then the value of the account after 1 year is going to be $2, right? Because 100% of a dollar is $1. So we get $1 of interest onto our $1, that's $2. So let's see what's going to happen as we apply interest more and more often as we change our compounding frequency. All right, so if we apply interest once a year, like we said, we're going to have $2. So let's take a look at where this came from. That's really just from our formula. So if I'm doing 1 year, my initial investment is $1, right, times 1 plus. So the rate, right, is 100%. And 100% as a decimal is 1.00. Right, so that's where that 1 is coming from, divided by n. N is our compounding frequency. If we're compounding once a year, that's 1. 2 to n is 1. And we're doing it for 1 year, 2 to 1 times 1. So everything's 1. There's a lot of 1s. And that, of course, is just 1 times 1 plus 1, which is 2. All right, so let's see what happens when we compound 2 times a year, when n is 2. So when n is 2, then that will be to the second power. All right, so it's really just this formula here that we're using. So when that happens, this is equal to 1.5 squared, which is 2.25. And that's actually really good. We get an entire 25 extra cents if we compound twice a year. All right, I was going to have you guys fill in most of this, but I just gave you the numbers. If you change that n into a 6, if you compound every 2 months, then we get like another, I don't know, another 27 cents almost, right? We're going up by 0.27 here. We're going up by 0.25. All right, so let's compound even more often. Let's take 1/12 of the interest, right? 1/12 of 100%, and let's do that 12 times a year. And let's see what that gets us. Have the number here. So if we do it monthly, it's going to be 2.613035. And now we're going up by, I don't know, about 9 cents. Then if we compound 100 times a year, if we change n to 100, now we're going up by like another 9 cents, it looks like. Then when we do 1,000 times a year, we're going up now by, oh, that's less than, well, that's about 1 cent. We're going up by about 1 cent. And then when we go from compounding from 1,000 times a year to 1,000,000 times a year, well, that's less than 1 cent. It looks like plus 0.0013-ish. Then we go from 1,000,000 to 1,000,000,000. Well, now we're only going up by plus 0.0000. 1, 2, 3, 4. There's 5 zeros and then a 2. So do you guys see what's happening? Like we're changing our compounding frequency. We're going from like 1,000,000 to 1,000,000,000. That's a huge jump, right? That's times 1,000 times. But the amount of change there is, it's really, really, really small. So again, we're trying to compound continuously. We're trying to make n infinitely large. So the question is, what's going to happen as n approaches infinity? And I'll tell you the number it approaches is e. All right, you're probably wondering, that's a letter, Mr. Chu. That's e. E is not a number. Well, this is a number. This is called Euler's number. Euler's number. And a long time ago, I think this guy called Bernoulli, and then followed up by Euler, they actually calculated this number. It's an irrational number. And this number is about 2.718 something, something, something. Right? It's an irrational number. There's an infinite number of decimals, but I just remember 2.718. So that letter E, it's a symbol, right? It's a symbol to represent this constant, this quantity. And we have a letter for E because it's quite important, right? It's when things grow continuously, this letter E, or this value of E, it's going to appear, right? It's just like how pi is used to represent 3.14. Right, now we have another famous mathematical irrational constant called Euler's number. Right, and if you want to Google real quick, you can Google just the digits of E, and it'll give you like 10,000 digits, just like they do with pi. Right, very famous number, and that's E. So we don't have the math to prove this, but it's just something you have to accept. I mean, you can just plug in larger and larger numbers. Of course, you can't plug in infinity, but if you could plug in infinity, this is what you would get. You would get this number, right? So in other words, we can say as n approaches infinity, well, what were we doing? We were plugging into this over here, right? 1 plus 1 over n to the n. We can say as n approaches infinity, 1 plus 1 over n to the n power approaches this value of E. And in fact, we can say it's equal to E if you want, when n is infinity. Right? And that again is around 2.718, something, something, something. Uh-oh. All right, I don't know what's going on. I'm getting like some weird message, but all right. Any questions so far? Is that good? All right, so E is this value we're getting as we compound continuously here. All right, so again, here's our compound interest formula. We can't use this when compounding continuously because you can't plug in an infinity into an equation, right? You can plug in a very large number for n to get an approximation, but that's not going to be good enough So we're going to get an exact continuous compounding formula. So over here on the side, I'm going to say 1 plus 1 over x to the x power as x approaches infinity, right, is equal to e. Right, and that again just came from this. All I did is I changed n to x. So I'm going to use this as like a placeholder. I'll write it the same way I wrote it before, right? As x approaches infinity, this is going to approach e, or this is equal to e. Just like before. All right. So I'm using a different variable here. I'm using x instead of n because n is already in this formula and I don't want to get mixed up. All right, so first thing I'm going to do is I'm going to say a equals p times 1 plus. I'm going to do some algebraic manipulation. These steps aren't going to make sense until the very end. So the first thing I'm going to do is I'm going to change r over n to 1 over n over r. All right, you don't need to understand why I do this. I just want you to see that these are equivalent. Right, this is a proof of our continuous compound interest formula. So the steps in this proof aren't going to be logical until the end. So I hope you guys agree that 1 over n over r, right, that is 1 divided by n over r. And we know division is multiplication by the reciprocal, so that's just 1 times r over n, which is r over n. Right, so I did not do anything to my original equation, right, my original formula. I didn't change it, like numerically or value-wise. I just changed the way it looks. It's still the same. Right, and the next thing I'm going to do is I'm going to raise this to the n over r power. And then I'm going to take this entire thing, let me change that to blue, and I'm going to raise this to the RT power. All right, so let's see what happens. I'm going from a power to a power. And we know the rule when I raise a power to a power is to multiply the exponents. So that's n over r times RT. And the r's cancel out. That's equal to NT. So isn't that what we have here? So I didn't change anything. Raising it to this exponent, that's the same thing as raising it to the power of NT, because when we multiply the exponents, power to the power, we get NT. So I didn't change that. And also, this part here stayed the same. Right, so these formulas, they are identical so far. So far, so good? Can I get a yes or no in chat, please? All right, cool. So hopefully you're noticing something inside these brackets. Inside those brackets, it looks like this. Copy, paste. Isn't that of the form 1 plus 1 over x to the x power? It's just instead of x, I have n over r. So I'm going to do a substitution here. I'm going to say, let n over r equals x. Right? And again, remember what we're trying to do. We're trying to get a compound interest formula when n goes to infinity. So what happens as n goes to infinity? Well, I can say, as n goes to infinity, what's happening to x? Well, if this is going to infinity, right, isn't x also going to go to infinity? It doesn't matter what the rate is. As long as n goes to infinity, x is also going to go to infinity. So once I do that substitution, I get a equals p to all of this to the RT power. Right? But as n goes to infinity, x also goes to infinity. And from what we discussed earlier from this table, right, as this value goes to infinity, 1 plus 1 over n to the n, or 1 plus 1 over x to the x, that is equal to the value of e. So here is our final formula. A equals p times e to the rt. And it's a very cute formula. It's PERT. A equals PERT. And this is what we get when we compound continuously. PERT, PERT, PERT. Very easy to remember. It's not on your reference sheet, but you do need to know this formula. And also, by the way, this is also not on your reference sheet, so you should also know this. But they sometimes give it to you in the problem if you need to use it, but you should know it. Cool? All right, I guess that's cool. So that is our PERT formula. And just so you know, in this formula, everything is a variable, right? Except for this letter E, right? That E, that's Euler's number again, that's a number, that's 2.718. So make sure you're not trying to plug something in for E. E is E. Right? Again, R is our rate, that's going to be our APR, or nominal rate. T is time in years, P is the initial amount, your principal, A is the amount you have after. All right. So on YouTube, this is probably where I would tell you to pause the video, but I don't want to make this video too long. So it's a good problem to try. Let's take a look at it. Kellyanne has $20,000 to invest. She puts half of the money into an account that grows at an annual rate of 0.9% compounded monthly. This is a Regents question, by the way. So she puts half of her money. All right, so she's investing 20 grand. Half of 20,000 is, all right, good job, guys. It's $10,000. So she's putting $10,000 into an account that grows at an annual rate of 0.9%. And this is compounded monthly. So it's not just giving us 0.9% once a year. They're giving us 1/12 of that interest rate 12 times a year. So for this piece, we can say she has 10,000, and that's 1 plus 0.009 divided by 12 to the 12th power. Right, that's how much you will have after 1 year for this investment. So after 1 year, I can do 12 times 1 for 1 year if you want. At the same time, she puts the other half of her money into an account that grows continuously. So when something grows continuously, we are going to be using our PERT formula, right? And in essence, what we're doing is we're plugging in infinity here, right? But that doesn't work, so we came up with our PERT formula. So her other half, for the continuous growth, she's investing another 10,000. That's going to be times E to the our rate 0.008 for 1 year. So just times 1. And that's how you can calculate the amount when it's growing continuously. Oh, so which function represents the value of Kellyanne's investments after T years? I don't know why I thought she put it in for 1 year, but if after T years, right, then that should be 12T, and that should be 0.008T. So we have to add both of these together. So it looks like they're doing f of t. So f of t is going to be the sum of this plus that. And I don't see any choice with 1 plus 0.009 divided by 12, but if you actually divide it out and add it to 1, that should equal 1.00075. And there's what we got for compounding continuously. So it looks like this is choice 4. Cool. All right. This doesn't feel like a live video if you guys don't talk to me. Very sad. It'd be nice if I could get some cools in chat. Or someone, I know some of you have mics, it's okay. All right, so that's pretty much it. That is compounding continuously. Just wanted to show you the PERT formula today and where it came from. Thank you, Wilson. But we also have these kinds of questions, which are very, very weird, to be honest. But this has been on the Regents a couple times. And, oh, thank you, Tanya. And you guys know the Regents has been canceled, right? For the end of the year. Very sad. I know. But yeah, these are Regents kinds of questions. They're hard ones, but let's take a look. All right. Jim is looking to buy a vacation home for $172,600 near his favorite southern beach. The formula to compute a mortgage payment M is given by that crazy looking formula. All right, so you guys might not even know what mortgage is. Well, a mortgage is a loan for a house. It has a special name because houses are expensive. So where P is the principal amount of the loan, it's how much you're borrowing. R is the monthly interest rate, and N is the number of monthly payments. All right, so Jim's bank offers a monthly interest rate of this, so that's our R value, for a 15-year mortgage. All right, if you have a 15-year mortgage, it means you're paying it off over the course of 15 years. So 15-year mortgage, well, that's going to give us our N value, which is the number of monthly payments. So if we're paying off this mortgage for 15 years, then it's going to equal 12 times 15. So you got to be a little careful. There is a unit change here. Make sure you're getting it in terms of months. So that is 180 months in 15 years. Right, with no down payment, determine Jim's mortgage payment rounded to the nearest dollar. All right, you also need to know what down payment means. Do you guys know what a down payment is? All right, well, a down payment is something you pay up front. So easier to think about with cars. So let's say you're buying a $20,000 car. So if you have no money, you need to borrow $20,000. You would take out a $20,000 loan, right? But if you put down a down payment of $5,000, well, then you only need to borrow $15,000. So a down payment is like an initial payment, so you have to borrow less money. It's gonna affect the amount of your loan. So in this case, the down payment is 0. So we need to borrow the full amount. You assume that if he's paying for this house with no down payment, he's not paying anything. So he has to pay the full amount. He has to pay $172,600. So that's gonna be the principal amount of the loan. It's how much he's borrowing. So let's plug everything into this formula. M is equal to P, which was 172,600, times our rate, 0.00305, times 1 plus 0.00305, all raised to the 180th power, divided by 1 plus 0.00305 raised to the 180 minus 1, close parentheses. Whew, that is crazy. So I'm going to open up my camera just to show you how I type it in on my calculator, because, yeah, it's hard to type it into the calculator. This is the hardest part of this problem, is typing it into the calculator, to be honest. So, camera. All right, I don't know if you guys can see that or not, but all right, I'm gonna try my best. Hello, guys. Let me know if this setup is working. So what am I typing in? I am typing in 172,600 times. All right, I'm gonna hit Control Divide. Control Divide, you got that, 0.00305 times 0.00305 times, in parentheses, 1 plus 0.00305, close parentheses, all to the, all right, something is going wrong here. All right, guys, this is pretty difficult. I'm holding my iPad in one hand, and then trying to calculate with my other hand. So that is 2 to the 180th power divided by 1 plus 0.00305, close parentheses, 2 to 180 minus 1, and hopefully if I did this all correctly, bam, 1247.49. 1247.49. All right, and the reason I typed it all in one and then like evaluate the numerator and then the denominator is if you don't get enough decimals, you're not going to be accurate enough. And in this problem, you have to be very accurate because look at this decimal, that's 0.49. If you got like 0.50, then you're going to get the wrong answer because it says to round to the nearest dollar. So if I round, I have to round down, and that is my monthly mortgage payment. Bam. All right, so here's the harder part of the question. Actually, I didn't get rid of all my notes. Delete that. All right, here's the harder part of the question. Algebraically determine and state the down payment rounded to the nearest dollar that Jim needs to make in order for his mortgage to be $1,100. All right, I'm going to copy and paste all of this. So copy, paste. So this time in this problem, he doesn't want to pay $1,247 a month. He thinks that's too much. So he wants to make monthly mortgage payments of $1,100. So this M here is going to be $1,100. And now we want to solve for the down payment, but there is no variable in this equation anymore, right? So where is the down payment going to go? So remember, the down payment is the amount you pay initially. That's going to affect the amount you need to borrow. So your down payment, it's going to come out of this initial loan that you need to borrow, right? Remember the car example. If you put down a down payment of $5,000 on a $20,000 car, then you only need to borrow $15,000. So this amount he's borrowing, we can subtract the down payment to get the actual amount he needs to borrow. So this is what we're trying to solve for. We're trying to solve for this down payment, and there's our equation. So again, that's a crazy looking equation. I'll show you how you can type this in your calculator. So going back to our calculator, bam, adjust, all right. We're gonna do 1,100 divided by all of that. Let me go back. All right, so what I'm gonna do in my calculator now is I'm gonna divide both sides by this quantity. Let me copy and paste this. Copy, paste. All right, I'll divide the right side by this. And so I have to divide the left side by that quantity. So I'm going to type it in exactly like this in my calculator. So let me show you what that looks like. How do I do this again? Plus camera. So I'm going to do 1,100 divided by, well, actually, you know what? I'll make this a fraction. So I'm going to do control divide 1,100 divided by another control divide. And I'm actually going to copy and paste this. Well, never mind. How did I do this last time? I'm just going to copy and paste this. So just highlight it and hit enter. And I don't need the 172,600 part. So I'm just going to get this value. Hit enter. It's equal to that. And I'm doing 1,100 divided by this value. So if you highlight this, it's actually going to give you all the decimals, so it's accurate enough. Bam. And so that's 152,193. And let me get some decimals near a cent. 152,193.19. So if you typed it in for part A, you can use that to help you with part B here. So what was that equal to? 152,193.19 should be good enough. And that's because we're rounding to the nearest dollar. So at this point, if I have that, that should be close enough. 172,600 minus our down payment. And now from here, it's a very simple algebra equation. All right, let's subtract 172,000 from both sides. That's going to be negative 2406.81 equals the negative value of the down payment. Right, we could have used a letter for down payment like D. All right, but I decided to write it out for our first time. So our down payment to the nearest dollar is going to be equal to $20,407. In other words, he has to pay $20,000 on this 172,000 house if he wants to make monthly payments of $1,100. All right, cool. And that's how you deal with these crazy looking problems. The formula might be different depending on the question, right? But that is what they mean by down payment. That's going to affect their principal amount of the loan, how much you need to borrow. So even though it's not in the formula, you need to know how to put it in. All right, so today we did a weird problem like this, and we also talked about compounding continuously, which is just this PERT formula. All right, so that's it. You guys are free if you want to go. If you have any questions on anything else, I'll do like a mini extra help session right now. So if you have no questions, I'll see you guys later. If you want to hang around, ask me any questions you have.